Andreas Fault is well known to most people. It's an 800-mile-long monster that severs California from south to north as two tectonic plates grind against each other, threatening large earthquakes. It's something that has already come to pass in the past, and residents have been warned again that another calamity is just on the horizon. In fact, the earthquake comes every 22 years, with the last one having occurred in 2004. If the past is any indication, another one may be closer than any Californian would like it to be. There's a crack in California that's 800 miles long. Stretching from the Salton Sea in the south to Cape Mendocino in the north, it crosses vineyards, subway stations, power lines, and water mains. Millions of people live and work alongside the crack, with many crossing it daily by using the 966 roads that cross the line. Most people don't give it a second thought, but in reality that crack, the San Andreas Fault Line, has the potential to destroy lives and cripple the national economy in an instant. Thomas Jordan, the director of the Southern California Earthquake Center, recently made an announcement that should have sent shivers down the spines of all Californians. The San Andreas Fault appears to be in a critical state, and as such, a large earthquake is imminent. This isn't the first time Californians have been reminded about the impending threat, but the warning that the southern portion of the fault looks like it's locked, loaded, and ready to go is. So why is this eminent seismologist making such dire predictions? In fact, there hasn't been a significant release of stresses in the southern portion of the San Andreas Fault System since 1857. In layman's terms, the San Andreas Fault System is one of many that roughly marks the boundary between the Pacific and North American tectonic plates. Both plates are moving northward, but the Pacific plate is moving faster than the North American plate, implying that stresses between the plates are constantly increasing. Some of these stresses were catastrophically released in the San Francisco Bay Area in 1906 in a 7.8 magnitude earthquake, and again in Northern California in 1989 in the 6.9 magnitude Loma Prieta earthquake. Fortunately, events of this magnitude have not occurred along the San Andreas Fault in the state's south since then, though the 1994 Northridge event was associated with a nearby but separate fault system. However, this lack of quakes has raised the possibility that one is on the way, and that given the amount of stress that may have accumulated, it will be the big one when it arrives. So how large could this potential earthquake be, and is it possible that the destruction depicted in the film San Andreas could actually occur? In short, the answers to these questions will satisfy Californians to some extent. In the film, the San Andreas Fault causes a 9.0 magnitude earthquake. While not unheard of on a global scale, earthquakes of this magnitude are typically confined to areas of the Earth where subduction, the movement of one tectonic plate beneath another, is occurring, such as Chile and Japan. California's tectonic situation is unique. Two plates are sliding past each other here. As a result, many predictions limit the maximum earthquake magnitude along the San Andreas Fault System to 8.0, with a 7% probability estimate that such an event could occur in Southern California within the next 30 years. Also, there is a 75% chance of a magnitude 7.0 event occurring in the same time period. While magnitudes of 7.0, 8.0, and 9.0 may appear insignificant, the energy released by such events varies a lot, with a magnitude 9.0 event releasing 32 times more energy than a magnitude 8.0 event and 1,000 times more energy than a magnitude 7.0 event. Obviously, whether a 7.0 or an 8.0, the damage is unavoidable, but the entire sequence of events depicted in the Dwayne Johnson movie is improbable. For example, because the San Andreas Fault is not beneath the ocean, any slippage along it could not displace enough water to cause a tsunami. The formation of a massive chasm is also from the realm of fantasy, as the plates are sliding relative to one another rather than away from one another. What is realistic is that a significant amount of destruction is likely. While California's building codes are stringent, recommending seismic protection measures for older buildings and prohibiting the construction of new buildings near known fault lines, there is no way to make a building completely safe from the looming natural disaster. To better understand the effects of such an event, it's also necessary to gain a full understanding of the fault zone. So how many fault zones are there? There are 3 of them: the northern, the southern, and the central. The northern segment of the fault runs from Hollister through the Santa Cruz Mountains, which is the epicenter of the 1989 Loma Prieta earthquake, then up the San Francisco Peninsula, where it was first identified by Professor Lawson in 1895, and finally offshore near Muscle Rock in Daly City. This is the approximate location of the 1906 San Francisco earthquake's epicenter. The fault resurfaces at Bolinas Lagoon in Marin County, just north of Stinson Beach. From there, the fault returns underwater through to Miles Bay's linear trough, which separates the Point Reyes Peninsula from the mainland, runs just east of Bodega Head through Bodega Bay, and then back underwater, returning onshore at Fort Ross. And there are several significant sister faults that run more or less parallel in this region around the San Francisco Bay Area, and each of these can produce significantly destructive earthquakes as well. The northern segment continues overland from Fort Ross, forming a linear valley through which the Gualala River flows in part, and then it returns to the sea at Point Arena. Following that, it runs underwater along the coast until it reaches Cape Mendocino, at which point it begins to bend west and ends at the Mendocino Triple Junction. Then there's the San Andreas Fault's central segment that runs northwest from Parkfield to Hollister. While earthquakes occur in the southern section of the fault and in parts of Parkfield, the rest of the central section of the fault exhibits a phenomenon known as a seismic creep, in which the fault slips continuously without causing earthquakes and was created by a transform boundary. Finally, the southern segment, also known as the Mojave segment, begins in California near Bombay Beach. Upturned strata associated with that section of the fault can be found in Box Canyon near the Salton Sea. The fault then runs along the southern base of the San Bernardino Mountains through Cajon Pass, and then northwest along the northern base of the San Gabriel Mountains. These mountains, known as the Transverse Range, are the result of movement along the San Andreas Fault. A section of the fault is visible in Palmdale at a road cut for the Antelope Valley Freeway. The fault runs northwest along Elizabeth Lake Road until it reaches the town of Elizabeth Lake. As it passes the towns of Gorman, Tejon Pass, and Fraser Park, the fault begins to bend northward, forming the Big Bend. This restraining bend is thought to be where the fault locks up in Southern California, with a 140 to 160-year earthquake recurrence interval. The fault then runs northwest of Fraser Park through the Carrizo Plain, a long, treeless plain where much of the fault is clearly visible. The Elkhorn Scarp runs the length of the fault trace within the plain. Now, it's widely known that an 8.1 magnitude earthquake could strike the southern segment, which stretches from Parkfield in Monterey County all the way to the Salton Sea. This fault runs about 35 miles northeast of Los Angeles. A large earthquake in this southern segment would kill thousands of people and cause hundreds of billions of dollars in damage in Los Angeles, San Bernardino, Riverside, and surrounding areas. However, once the fault's location was identified, scientists still had to do more work in order to better understand the effects of a large southern San Andreas earthquake. So the U.S. Geological Survey created a 7.8 magnitude event with a slippage of 2 to 7 meters to represent the stresses that have accumulated in the area since the last large event, also known as the shakeout scenario. Based on this model, it was determined that the constructions straddling the fault would sustain the most damage. Fortunately, after the 1972 Alquist-Priolo Earthquake Fault Zoning Act, such structures are few and far between. This slippage, however, would affect the 966 roads, 90 fiber optic cables, 39 gas pipes, and 141 power lines that cross the fault zone. The total cost of building damage was estimated to be in the tens of billions, somewhere around $33 billion, with modern buildings faring well but older buildings particularly vulnerable. Fires would rage as they did after the Northridge earthquake, as gas mains and mains water pipes would be severed during the catastrophe. In fact, the damage from the resulting fires is estimated to be more costly than that resulting from the initial shaking. The total death toll was estimated to be 1,800. And just when you think things can't get any worse, the main event will have destabilized the region's tectonics to the point where a series of potentially powerful aftershocks would begin. For example, in 2011, Christchurch, New Zealand was hit by a 6.2 magnitude earthquake, and the city and surrounding region have since experienced over 10,000 aftershocks. Fortunately, the film San Andreas is pure fiction, with the exaggeration we've come to expect from filmmakers who, ironically, are also based in Southern California. Nonetheless, the San Andreas fault will almost certainly produce a significant earthquake in the not-too-distant future, and when it arrives, the damage will be severe, and Southern California will be severely impacted. However, Californians are no strangers to these occurrences, and the state's infrastructure has recently been designed with earthquake protection in mind. Of course, to deal with the possibility of a future earthquake, NASA has gotten involved too. In fact, their radar offered a 3D aerial view of the San Andreas fault. You see, the Earth's crust is made up of fractured plates that move across its surface over millions of years. Two major plates collide off the coast of California. The Pacific plate is slowly drifting northwest and grinding along the margin of the North American plate to the east. The intense pressure of this collision is what created the 800-mile-long fracture zone known as the San Andreas Fault where they meet. A distinct trough runs along the length of the fault, and the Crystal Springs Reservoir fills the trough that marks the underlying fault in this false-color NASA radar image of the fault west of San Francisco Bay. I-280 curves along the east side of the fault, and California Highway 92 heads west towards Half Moon Bay. The image was taken in November 2008 as part of a campaign to collect detailed, three-dimensional images of the San Andreas Fault along the same flight path on a regular basis. The goal is to map which parts of the fault are creeping past each other with little stickiness and which appear to be locked together, places where pent-up stress could be suddenly released in a major earthquake. Scientists can identify places where the topography is visibly deformed by repeatedly collecting images over an identical flight path. Ground deformation, which can be as small as a fraction of an inch, can indicate that the plates are stuck together far below the surface. Now, the San Andreas Fault is divided into three major sections that can move independently, as we mentioned earlier. NASA learned that the plates in all three are attempting to move past each other in opposing directions, much like two hands rubbing against each other. Much of the time, the plates in the southern and northern sections are locked, stuck together in a dangerous, immobile embrace. This causes stresses to accumulate over time, whether it is years, decades, or centuries. Finally, however, a breaking point is reached. The two sides lurch violently past each other, and an earthquake occurs. However, in the central section, the plates slip past each other at a pleasant, steady 26 millimeters or so each year, and in doing so separate the other sections, preventing a massive earthquake from occurring. At least, that's what most scientists have been saying so far. However, a new study of rocks drilled nearly 2 miles beneath the surface suggests that the central section has been the site of numerous major earthquakes, some of which may have been relatively recent. The research, which employs new chemical analysis methods to measure the heating of rocks during prehistoric earthquakes, was recently published in the online edition of the journal Geology. According to lead author Genevieve Kofi, a graduate student at Columbia University's Lamont Doherty Earth Observatory, this meant that larger earthquakes could occur in the central section than was previously thought. Everyone should be aware of the possibility that it's not always just continuous creep. The San Andreas Fault poses numerous dangers. The northern section was the site of the devastating 1906 San Francisco earthquake, which killed 3,000 people and leveled much of the city, while the 1989 magnitude 6.9 Loma Prieta earthquake killed over 60 people and destroyed a major elevated motorway. And the southern section was responsible for the 1994 magnitude 6.7 Northridge earthquake near Los Angeles, which killed approximately 60 people. And many scientists believe it's storing energy for an event on the scale of 1906. The central section, on the other hand, appeared to be harmless. Only one small area near its southern end is known to produce genuine earthquakes. Their magnitude 6 events, not particularly dangerous by most standards, occur every 20 years or so. Because of their frequency, scientists hoping to study clues that may indicate an impending earthquake has established a major observatory atop the fault near the city of Parkfield. It includes a 3.2-kilometer deep borehole from which rock cores were extracted, as well as monitoring instruments both above and below ground. Coffey and her colleagues examined a rock from near the bottom of the borehole. When earthquake faults slip, friction along the moving parts can cause temperatures to rise hundreds of degrees higher than the surrounding rocks. This heats the rocks, altering the organic compound makeup of any sedimentary formations along the fault path. Pratigya Polasar and Heather Savage, study co-authors, recently discovered how to exploit these so-called biomarkers by using the altered compositions to map prehistoric earthquakes. They claim that by calculating the degree of heating in the rock, they can identify previous events and estimate how far the fault moved. From this, they can extrapolate the sizes of resulting earthquakes. They refined the method at Lamont Doherty in the United States Northeast, Alaska, and off the coast of Japan. The researchers discovered many such altered compositions in a band of highly disturbed sedimentary rock between 3,192 and 3,196 meters below the surface in the new study. They claim that the blackish, crumbly material contains evidence of more than 100 earthquakes. The fault appears to have jumped more than 1.5 meters in the majority of cases, which would imply a magnitude 6.9 earthquake, similar to the destructive Loma Prieta and Northridge events. However, many of them could have been larger, according to the researchers, because their method of estimating earthquake magnitude is still evolving. They believe that the quakes along the central section were similar to other large San Andreas events, such as the one that destroyed San Francisco. While this is a surprise, the current official California earthquake hazard model, which is used to set building codes and insurance rates, does allow for the possibility of a large central section rupture. However, given the lack of evidence for any such prior event, the inclusion of this possibility was arrived at through mathematical calculations and was pretty controversial. The new study appears to be the first to show that such quakes have occurred in the area and offered proof when there was none before. According to the authors, they could have started in the central section or, more likely, started to the north or south and migrated through the central section. So when could these earthquakes have occurred? Trenches dug by paleoseismologists across the central section revealed no disturbed soil layers that would indicate surface quakes in the last 2,000 years. In geologic terms, however, 2,000 years is a blink of an eye. Furthermore, the excavations may have missed a number of quakes that did not necessarily rupture the surface at specific locations, so nothing's very clear at the moment. To answer this question, the researchers used a second novel technique. The biomarkers are found in very narrow bands, ranging from microscopic to a few centimeters wide. Only a few inches or feet away, the rock heats up enough to drive out some or all of the naturally present gas known as argon. Other scientists have long used radioactivity to determine the ages of rocks, which was also convenient for the authors. Simply put, potassium decays into argon. The greater the ratio of argon to potassium, the older the rock. As a result, if some or all of the argon is driven out by earthquake-induced heat, the radioactive clock is reset, and the rock appears younger than the identical, nearby unheated rock. This is precisely what the team discovered. They studied sediments that formed tens of millions of years ago in an ancient Pacific basin that was subducted beneath California. The potassium-argon clock revealed that the ages of rocks surrounding the thin quake slip zones were as young as 3.2 million years. This provides a time frame, albeit a hazy one, because scientists are still unsure how to assess the amount of argon that was driven out, and thus how thoroughly the clock may have been reset. In turn, this means that the most recent quakes could have occurred as recently as a few hundred or thousand years ago. The team is currently working on a new project to improve age interpretations and find accurate answers to their questions. The authors concluded that their work ultimately highlighted the importance of including the central part of the San Andreas Fault and other creeping faults in seismic hazard analysis. Only then could they get a full picture of what was happening. Now, all of this may sound scary, but scientists are far from worried. While a possible large quake is included in the state's official hazard assessment, William Ellsworth, a geophysicist at Stanford University, who has led the research at the drill site, believes that most of them think that they happen rarely, as tectonic strain is not accumulating at significant rates, if at all, at the present time. According to Morgan Page, a seismologist with the U.S. Geological Survey who co-authored the hazard assessment, the study is groundbreaking. The creeping section is a difficult place to study because earthquake evidence is easily erased by the creep. She explained that if a large earthquake can tear through the creeping section, it means that a large earthquake could start at the very southern tip of the San Andreas, travel through the central section, and continue all the way up to the end of the northern section, the so-called big one that people like to speculate about. Page was excited about the new evidence and was hoping that scientists would use it to improve their model. And this brings us to the most important question: just how concerned should Californians be? Stephen Cox, a geologist at Lamont Doherty and study co-author, said, "People should not be concerned. California's building codes have improved, and let's face it, seismic activity is unavoidable. Not to mention the scientists were working to determine the most significant possible event and assist everyone in preparing for the worst." But while these words are reassuring, people are concerned. Not to mention climate change has made things far worse. Droughts have parched many parts of California in recent years, contributing to widespread wildfires that are difficult to control and take days, weeks, or months to extinguish. Recently, the Center for Climate and Energy Solutions released a drought monitor map depicting drought areas in the United States. Central and Southern California has been particularly hard hit. According to the study, climate change increases the likelihood of a worsening drought by increasing evaporation rates, which dries out soils, and decreasing precipitation. The study discovered that annual precipitation in the southwestern United States has been decreasing since the early 1900s and is expected to continue. If the area affected by the big one is suffering from a drought at the time of the quake, the fires that follow the quake and each aftershock could be even more devastating. According to Jones, the 2008 shakeout scenario predicted that the quake would cause up to 1,600 fires, in addition to the expected mass casualties and financial loss. If California continues to experience severe drought, as it has in recent years, fire damage could be worse than predicted. Climate change increases the likelihood that we will not have a cool, calm day and that residents would experience extreme fire conditions. This will only lead to further chaos. And 2023 hasn't started off any better. Soledad was hit by a quake mere hours before the start of the new year, and Humboldt County was jolted awake with a 6.4 magnitude tremor only a few days before that. While many were warned in fair time, those at the epicenter only had seconds to decide what to do. The fact is that even after such a large effort to understand the seismic activity under California,